So welcome to the fourth and last lecture in the series of model-based fault diagnosis. So as a last part, we are covering the issue of learning an unknown fault and presenting a simple example. So as in the previous lecture, now we are covering this part of our chain, so fault isolation and estimation. And we assumed that we were going through this step, the isolation step, but what happened is we falsified all the n fault hypotheses corresponding to the n faults that we know. So we end up with a case that we need to identify a new model for this new unknown fault. And this is accounting for the approximator part in the estimator that we called Fdft. And you will see it is the estimator we already know, the one with fault detection, with an additional part. Okay, so let us start from what we already have. So what we have is the class F. And the fault in the class F are parameterized in this way. So a given fault function has all its components written down as a parameter vector theta multiplying a structure function g. We did that because we know the functions g, so we probably have defined them using first principles. And the fact that we parameterized them linearly was helping us in the definition of the learning law that we use for estimating the parameters and also for computing a threshold. Now, how can we have a similar thing for an unknown fault? Well, this is quite a tricky question because if the fault is unknown, how can we have a parameterization for that? Well, we cannot have a specific parameterization because it is unknown. So we need to use a parameterization that is general, something that can be used to approximate pretty much everything. And so if you look in our arsenal of parameterized models that are general enough, well, we can resort to things like polynomials or neural networks, for instance, radial basis function networks or wavelet networks or other kind of decompositions like we mentioned before, Fourier or other similar basis-based decompositions. And this is what we're going to do. So we are introducing a new fault function that we call now phi hat 0 that is going to be parameterized by a parameter theta 0, but in this case the shape function is something general. So in the case of the Fourier analysis, we already defined that g should be equal to different trigonometric functions. If you have radius basis function, then g is made up of the activation functions of each neuron that is an exponential, and so on. One thing with that is we cannot guarantee that this is going to be linearly parameterized. In some cases, it is. So if you take a neural network where the center of neurons is fixed and only the amplitude is a parameter, then you get a linearly parameterized function. But in other cases, you don't. So the only thing that we can do is anyway to define the gradient with respect to parameters in this way. We just write down the definition of gradient. So it is the partial derivative of phi over the parameter theta hat. And we need this because we are going to implement a learning law that is similar to the one we already implemented. So before talking about the learning law, we need to define how we are using this new function that we introduced. So this approximator for the unknown fault. Well, we introduced that in an estimator, as we did before, but as anticipated, we introduced that into the fault detection approximator. So the one that we use for fault detection, after a fault has been detected, we'll get a new term, this one, that will be used to approximate a possibly unknown fault. And indeed, the key part is that this term will be turned on only after detection. And that should not come as a surprise why we're doing it. So now if we look at the observer and the estimator, it is functionally equivalent to one of the fault isolation estimator. The difference is that we have this approximator here that is a general one. This is the only difference. Now that we have this approximator that depends on a parameter theta hat 0, we need to devise a learning law for that. But now everything that is written down here should not sound unfamiliar to you, because it is almost exactly the same learning law that we had for the fault isolation estimators. So the only difference is that now the gradient is written out here generally as z, which can then be a function of the parameter itself, as the function phi is not assumed to be linearly parameterized. And in computing the learning rate, when you normalize by the norm of z, we are using a slightly different norm. We are using the square of the Frobenius norm, not the Euclidean norm as we used before. And so the Frobenius norm is, the square of it is the sum of the square of the terms on the diagonal. So Z is a matrix in general, because phi is a vector, the parameter theta is a vector, so when you compute the partial derivative, you get a matrix. And then the Frobenius norm is the sum of the square of the terms on the diagonal matrix here. But apart from that, everything is the same. We also have the projection operator here. So a tricky thing is that the projection operator requires to define a domain for the parameter theta. So for a fault that is unknown, there is no way to define these exactly and give some physical sense to that. So the only thing you can do is to have some reasonable over-conservative estimation for this, considering what is the worst case that can happen based on physics. So you need to have some insight in the way your system can work and what is the absolute limits of the dynamics. Of course, it doesn't make sense for a fault function to have unbounded values. But it can happen that if you choose this too small, you basically will see your parameter that is always on the boundary on that without being able to approximate the fault function efficiently. So it may require some trial and error. But the thing is that this is defined in order to run online, but you can also run that on a time series of data that you recorded. So if the choice you made initially for this theta hat, or the choice that you made initially for the structure of your approximator phi 0, they are not good, you can try another one on recorded data. So now that we presented this, we can go through a simple example. And again, we are using the 3 tanks benchmark. So these are the equations that we already seen in a previous lecture. So you remember that we have the 3 tanks, and the number 3 is the one in the middle. And we are assuming our fault class includes 3 faults. The one is the first pump shut down, the second is a leakage in tank number 1, and the third is the pump number 2 shut down. So pump shut down means that the term U1 that you have here, instead of being the one that you intended, will be one that is reduced. So it is like saying that you have a U tilde 1 that is equal to the same parameterization we introduced many times. So 1 minus some amplitude that multiplies U1. So we can write that in the formulation we introduced, and it corresponds to having a function phi 1 that has second and third component null, because this equation and this equation are untouched by the fact that the pump number 1 is failing. So we have only the first component here that has only one parameter and only one shape function. And the parameter is A. Well, I used alpha, but here I use A, sorry. And the shape function is minus t over A that multiplies u. And indeed, if you look at the previous equation, here you have u that is multiplied by t over A. So when you have your fault, so let us make this A. So when you have your fault, you end up having minus A u1 multiplying t over A added on top of this. So this is the fault function. Similarly, for the pump number 2 shutdown, we have a fault function phi3 that is only affecting the second equation and has exactly the same parameterization as the first one. So the thing that is different is the leakage in tank 1. So again, tank 2 and 3 are unaffected. What we have is a term here that is equal to one parameter defining the area of the leakage. So let us assume that in the tank that has some level of the liquid now equal to H. Oh, sorry, we denoted it X1. So the level for tank 1 is X1. And in the bottom, we have a leakage, a hole, through which additional water is flowing out. So the parameter here, theta, is defining the cross-section of this hole. So we assume it is a circular. We assume it has a radius ρ1, while the area of this is ρ1 squared by pi. So these represent the area of the leakage. And this is the function telling us how much water is getting out through a leakage of unitary cross-section. So we have still this ratio here that is due, well, to the fact that we are in discrete time, to the fact that the total cross-section is A1. And this term here is 2 times G, the level. So actually, by conservation of energy, this is telling us what is the velocity of the water flowing out through this hole. So the velocity of the water multiplied by the cross-section through which it is going, it is giving us a volume flow out of the leakage. So this is the way to parameterize. And indeed, whatever the size of the leakage, still this is going to be the velocity of the water flowing out of that. And the only thing that is changing is the cross-section here. And so this is an example that is nice because you can easily see how you get a linearly parameterized fault function and how you write the shape functions for these cases. So this was applied to the same experimental 3-tank system I shown you before. So we have the same nominal parameters as in the previous lectures, the same uncertainties of the parameters, and we model the same fault. So the leak in tank 1, and this time this time I also have here the size of that. So it is a size of 0.2. So if you look at the output from the fault detection approximator estimator, where we see exactly the same plot that we have seen before. So we have the residual before that is small, then you have this peak in the residual that is big enough to cross the threshold. But then the residual is going small again because basically the observer now is tracking the faulty behavior as well. In the case of the 2 isolators, so we expect number 1 and number 2 to be excluded. And indeed, this is what's happening. So for the first estimator, we have the residual is just getting big enough to cross its own threshold here, and you get a rejection. And actually, this was tricky because this is the other fault estimator that is modeling something occurring to tank number 1. So there is a chance that for this case, the fault mismatch function is small, because you have two things occurring on the dynamics of tank number 1. And so it makes sense, you can imagine that in some condition, a shutdown of pump number 1 or a leakage in tank number 1 can look the same, because they are both leading to the level of tank number 1, not increasing as it should or decreasing. But in this case, probably because of the size of the leakage or the timing of the leakage, we got exclusion. For the second, well, we expect not to reject the second, because the second is the one that is actually matching the fault, and indeed this is occurring. So we have the residual that is increasing, but the threshold in this case is quite bigger, and so we don't have exclusion. So you can see that the residual in the two cases is pretty much the same, but it is the threshold that is making the difference. So, and why? Well, this depends on the shape function that we are using and the domain of the parameters that we defined. Basically, the physics of the fault in the system. Then we have the number 3. So number 3, if we look at component number 1, we also have exclusion. And it is still just by a little bit, but maybe more than in the first case. Anyway, we are in the ideal case. So we rejected the hypothesis 1 and 3, and we are left with hypothesis 2, which is indeed what was happening in reality, which is very nice. So if we look at the approximator for that fault, so if we look at phi hat 2, this function, we get this behavior. So in green, we have the actual fault function that we computed afterwards using data. And here we have the approximated one. And the approximated one, well, initially it is going the wrong direction, but as soon as we start to learn the parameter, then it is getting closer to the true one. Still, there is some difference. It is not exactly that. There is some difference here. And the reason for this difference is, well, the key to answer that is to remember what is the dynamics of the residual. The dynamics of the residual is not just driven by the estimation error, but as we said, it is also driven by other terms that we can't get rid of. But the learning law doesn't know that. So the learning law is trying to make the residual the smallest possible. And in doing so, it is learning an approximated function phi hat that is compensating also for those other terms. So basically, this is smaller, maybe because it is accounting for uncertainty in the parameters that we use for the nominal dynamics, or it is accounting for measurement error. By the way, you see that this is not a very big one, so we are quite happy. Now, if we look at the behavior of the parameter that we are learning, theta hat 2, as you remember, we said that the nominal value of theta is 0.2, and the estimation we get is actually getting here. And so that's a wonderful result. So maybe there is some small difference, but we are close to be there. Okay, so this last lecture was shorter. We already introduced everything, almost everything in lecture 5.3. So today was just based on most of the things we have seen in lecture 5.3. So we presented how to learn an unknown fault, which turns out to be similar, equivalent to the way you learn a known fault. You just need to introduce an approximator that is general enough. And we presented an example. So this was the last lecture about the fault diagnosis. So from the next series of lecture, we are going to cover fault tolerant control.